Okay, I hope you can see the screen. So you can see the slide on global mean temperature, right? Let's start. So today's or this week's topics cover the domain of climate modeling. Given certain condition, certain initial condition, and considering taken into consideration different factors into account, how we can predict different variables in the Earth. For example, temperature, might be precipitation, might be the humidity, might be the wind patterns, and many more, which are related to this geographical or geological or geophysical world. So, first, I have a few questions, but before that, so this is the picture of the global mean temperature of the middle troposphere, and this is taken from this particular paper cited here. And here, the model we have used a model to determine the temperature that is shown in black. And this you can see the gray colors there. The model shows or different models show different outputs, and the black one is the average of the different outputs. So it is mean or average of the different outcomes of the model. And blue one is the observed temperature that actually happened during the time period of 1980 to 2050. So here you can see a clear increase of the temperature. Even if we extend this or take the time before 1980, we will see steady increase in the temperature. So that is a clear indication of the global warming that is occurring here. Now, our methodology or our study is based on how to find the future temperature or any variable using the past data and the past trend. And of course, the equations of motions will be there. And some factors we will use in the model. So how well we can capture the reality that is happening here. That's what we try to do in the modeling studies. Okay, so it's a kind of prediction using the initial condition or the previous conditions. Now, here you can see that there are multiple outcomes which are shown in gray, and we have taken the black one, which is the mean of the output. Now, there is a reason why we have taken the mean, and you can see that the mean matches quite well with the observed trend, while the other outputs, they might match with the observation at some point, but mostly if you take any particular path, they do not match. So they sometimes become higher, sometimes they become very low, and they cannot continue the trend. That's why we have taken the mean of the outputs, and that is called ensemble mean. Okay, ensemble means collection of different elements. So here the outputs are there. So we have taken ensemble, and the different ensemble produce different outputs, and we have taken the mean to get the average value or average behavior of the output, and that's how we have derived the black curve, and it matches quite well with the blue one. Okay. Now there are a few questions related to the climate modeling. I mean, it is a very interesting topic, and of course, if someone develops a good model, it is always appreciated. So this was and this will be an active field of research, because no model, no model can be perfect because you cannot exactly capture all the processes from microscopic level to macroscopic and also planetary level on the same model. So that is a limitation of model, this modeling studies. But somehow,
एक्सक्यूज मी सर,
yeah,
सर हिंदी में करवा दो.
okay, yes, yes. So, okay, fine. I will explain the first slide in Hindi. So before that, I will just ask Arjun. Arjun, is this slide clear? I will explain in Hindi then. If you are here, uh, otherwise I will just repeat the slide in Hindi. Okay. Yeah. So yeah. तो बेसिकली इन दिस केस यहाँ हम क्या कर रहे हैं, हम ensemble मीन का बात कर रहे हैं. ensemble इज एक्चुअली इट इज अ फ्रेंच वर्ड, तो उसका हिंदी मुझे नहीं पता. पर क्या कर रहे हैं कि हम ये तापमान कैसा होगा कुछ सालों बाद, इसको हम जानना चाहते हैं. यही हमारे मॉडलिंग का गुरुत्व है और यही उद्देश्य है मॉडलिंग का. ठीक है, तो इसके लिए हम क्या कर रहे हैं, कुछ इनिशियल कंडीशन, प्राथमिक कुछ स्थिति हम मान रहे हैं और इसको हम आगे बढ़ा रहे हैं विविध समीकरण के साथ, डिफरेंट सेट ऑफ इक्वेशंस के साथ. ठीक है, डिफरेंट पैरामीटराइजेशन, तो अलग अलग, थोड़ा मतलब लगभग सेम ही है शर्त, पर थोड़ा बहुत अलग होना चाहिए और उसके द्वारा हम आगे बढ़ा रहे हैं और इसका हम मीन मतलब एवरेज ले रहे हैं. तो इससे हमको जो काला सा आपको जो लाइन नजर में आ रहा है, वो काला सा लाइन है आपका मीन, इसको हम आंसम्बल मीन भी बोलते हैं. और ये नील वाला जो आप देख सकती है, ये है ऑब्जर्वेशन, मतलब ये असल में जो डेटा है उसके द्वारा प्राप्त किया गया. आप देख सकती है कि ये काला वाला और नीला वाला जो है, इनमें काफी मिल है, ये लगभग एक ही तरीके का आचरण कर रहे हैं. तो यही हम, हमारा मॉडलिंग का उद्देश्य है यही, कि हम कितना बेहतर जो असल में हो रहा है उसको हम प्राप्त कर सकते हैं इसके द्वारा. और ये क्या कर रहे हैं, ये जो तापमान का वृद्धि हुआ है, जो टेम्परेचर इंक्रीज, उसको अच्छी तरीके से पकड़ पा रहे हैं. पर आप अगर इंडिविजुअल फैक्टर्स को कंसिडर कीजिए, अगर करें, तो देख पाएंगे कि कोई भी एक कर्व, ये जो ग्रे कलर का जो लाइन्स है, उसको अगर आप पकड़ेंगे तो कोई भी एक इसके आसपास नहीं आ रहे, मतलब शुरू से अंतिम तक. तो इसके लिए हम इसका एवरेज लेते हैं ताकि इसका जो बिहेवियर है, और मतलब मीन मीन मतलब एवरेज का जो बिहेवियर है, वो जो असल में दिखा गया है उसके साथ बहुत करीब आ जाए, उसको हम अच्छे से पकड़ पाए. ठीक है, इज इट फाइन अंकित?
यस सर.
ओके, या प्लीज आस्क मी व्हेनेवर यू feel any doubt. uh, Arjun, is it fine about the first slide on the temperature?
Yeah, it's fine. It's fine.
Okay, so we
It's
will
fine.
ask a few questions about this. The first question is, why an ensemble of models is required to predict the weather or climate? The reason behind that is we never know the initial condition. So in climate modeling, determining the initial condition is exactly not possible because there are limitations. Suppose you are measuring the temperature in particular area, but the area just maybe 1 kilometers surrounded by that, or beside that, that might have some different initial condition, maybe 0.1 degree Celsius higher in temperature, lower in temperature. Wind conditions might be different. Also, let's say in your area there is greenery, a lot of plants. Might be some area is urbanized, so there are houses, urban islands we call. So we cannot exactly determine the initial conditions. That's why the final output can also not be exactly obtained. So it is not a deterministic problem. There are uncertainties associated to that. That's why in ensemble, what we do is we take one initial condition and we take some perturbation added to it. So we just apply, let's say you take a temperature, the initial condition of 30 degrees Celsius, and you create many realizations of that using small perturbation, let's say 30.01 degrees Celsius, 29.99 degrees Celsius, 29.89 degrees Celsius. 30.05 degrees Celsius, this type of, not very far from the initial condition, but close to that, and evolve that, because there might be uncertainty, there might be inaccuracies in your instrumentation or in your observational data also. So that might lead to wrong results. And then we evolve that with respect to time using the physical equations. And at the end of the equation, at the end of the simulation, we just take the average of that, like this. So the average will give you better answer compared to the individual component. That is the let's say that is the essence of this ensemble modeling. So I will just explain it once. तो ensemble लेने का जरूरत क्या है कि हम exactly जो initial condition, प्राथमिक जो स्थिति है, उसको हम ठीक से गणना नहीं कर पाते हैं, थोड़ा बहुत अंतर हो ही जाएगा। तो इसलिए क्या करते हैं कि एक इनिशियल कंडीशन पकड़ लेते हैं, उसके आसपास थोड़ा परटर्बेशन देते हैं। जैसे हमने उदाहरण दिया कि तापमान 25 डिग्री सेल्सियस है, तो आप क्या करते हैं, कुछ कुछ रियलाइजेशन लेते हैं तापमान में भी, 25.01, 24.09, ऐसा कुछ लेके, 24.99, ऐसा कुछ लेके आप बहुत सारी इनिशियल कंडीशन बनाएंगे, और उसको आप ये जो समीकरण है उसके द्वारा आगे ले जाएंगे। ठीक है, तो उसके बाद जो हमें मिलता है उसका हम एवरेज लेते हैं, मीन लेते हैं। तो इसका जो उत्तर आता है ये वास्तविक में जो होता है उससे काफी मिलता जुलता है। तो यही है हमारा आंसम्बल मॉडल का गुरुत्व। ओके, आई कैन टेक
Perturbation is it given to a single variable or like
multiple
uh
variables.
multiple variable? Okay.
Yeah, I mean, if your system is multidimensional and your initial condition depends on multiple variables, then the perturbation should also be given to multiple variables.
Okay.
And they create a lot of realizations for that. That's why they require very high computation power for that. And then they just do the average. So that is, for example, you might have seen a track of the cyclone, right? So in the track of the cyclone, they give some cone of uncertainty. I let's say, especially in the, I mean, in West Coast also, in Kerala also, cyclones happened in the past, right? So in the East Coast, it is more prevalent. So what they do is they will take the initial condition and they will part of that condition a little bit, such that a cone of uncertainty will be formed. For example, a cyclone is passing, they might tell that, okay, the cyclone might hit somewhere in between, let's say, Ernakulam and Kozhikode, like something like that. So it cannot be exactly that it will pass through maybe 10 degrees north, 70 degrees east, like that, but they will give a range in which it will pass. So that is the uncertainty that is developed, assuming the
So is there a probability like at a single point, like coast of Kozhikode, it'll hit with a probability like that?
so
Something like that? Or?
in probability, they actually what they do is for a single location, I mean, they will specify a range of location. From this to this location, the probability is very high. Let's say 75 to 100%. From this to that location, it is 50% or less than 50%. That's how uh, they announce the forecast. And when it comes closer to the coast, the probability, I mean, they're more sure, they become more sure, confident about where it will hit. So at that, I mean, one cannot exactly say that it will pass through that point of Kozhikode or that point of that coast, but they will specify a range, maybe 5 kilometers
Okay.
range. And with respect to time, the range becomes narrower, so they become more certain. So let's say the cyclone is formed and after 5 days it is set to hit the coast. Then they might say that it might hit the coast anywhere close to the, I think, Karnataka Kerala border, or maybe Tiruvananthapuram, which is far south of the Kerala. So after 3 days they specify a range, let's say maybe 100 kilometers north of Kochi or south of Kochi. Maybe just the day before hitting the cyclone, they issue a forecast that it will hit very close to Kochi, something like that. So
Okay. Okay.
that's how. And they also use ensemble forecasting for that, because they are not sure exactly where it will hit. So a single, I mean, it is not a deterministic system. For example, you are throwing a ball at the wall and catching this. That is a deterministic system because you know the equations of motion very well. If there is only one particle, you can apply Newton's second law, and you can, I mean, of course, the friction will be there, some damping will be there, but you can easily understand the process. But in this case,
Yes.
it is not a single particle problem, right? So it is very chaotic, nonlinear processes are involved. That's why they require uh, far more complicated calculations, and they are also uncertain about the process. Now, we often blame the weather department for issuing wrong forecasts, but the uncertainty is inherent in the situation. So sometimes people cannot do better than that. So that is the problem.
Okay. Thank you.
So yeah, Ankit, Mukesh, is it clear about the ensemble mean?
Clear, sir.
Okay.
Yes, sir.
Okay. Then the next question is, I will ask. Okay, I will ask you, Ankit, Mukesh. Can you tell me what is the pH? You know about the pH value? What is pH value? You know what is the concept of pH?
Lower the pH, higher the acidic, right? Like
Yes, 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 yes. That is true. So yeah, acidic solution means lower pH. That is a measure to. That is a, I'd say, an unit, a unit. So to measure the presence of acidity, or there are different definitions of pH, but let's say the presence of H3O plus or H plus ion in the solution. So acidic means there will be plenty of H plus ions, hydrogen plus ions. So the pH will be lower, and higher pH will be defined by uh, less presence of H plus or some presence of OH minus ion or similar kind of thing. So basic solution or alkaline solution. Now, what is the value of the pH of the ocean? Do, do you know, Ankit, Mukesh, what is the value of the pH, average pH of ocean? Well, that is not a big deal. No need to remember. It is currently 8.1. So previously, before pre-industrial era, it was 8.2 and it has reduced to 8.1. So it indicates that due to carbon dioxide, release of the carbon dioxide, it has become slightly acidic compared to the previous value. I mean, 8.1 is little alkaline or little basic, you can say. But due to the presence of carbon dioxide, it was dissolved into the water and it formed carbonic acid, and due to that acidification the pH value has decreased slightly, and it is also expected to drop again, or it might become lower than this particular value. Okay, because there will be higher carbon dioxide in the atmosphere, and that will be dissolved and that will form carbonic acid, or let's say bicarbonate ion and H plus ion, and that more concentration of the hydrogen plus ion will make the pH lower, or it will convert the water into more acidic one. Okay. Is it clear, Ankit, Mukesh, or I shall explain? Okay. Okay. If fine, then the next question is, why do climate models show higher ocean temperature than observed in the coastal regions? Okay, so there is a question. Climate models predict the ocean temperatures in different outputs, and it often shows that the ocean temperature is higher in the coastal area compared to the नॉर्मल वैल्यू और द स्टैंडर्ड वैल्यू जो सामान्य मान है तापमान का, उससे मॉडल का जो आउटपुट निकलता है वो थोड़ा ज्यादा दिखाती है। अब इसका कारण क्या है, मॉडल में हर हर एक बार ये क्यों होता है, ये सवाल है। So there are certain things in models which is known as bias. No matter whatever you do, there are certain characteristics or certain properties that will be there. For example, the ocean bias is there. In the coastal regions, the temperatures are higher than the normal value. Now that cause, that phenomena can be attributed to the upwelling. So the model resolutions are mostly not good enough. Now they are releasing high resolution model, but mostly they are not good enough to capture the upwelling that happens at the coastal regions. So in the coastal regions, what happens is the water from the beneath the surface that comes above, and the water which is beneath the surface is generally colder than the water which is at the surface, because if it is hotter, then it will be less dense and it will be situated towards the upward side due to the buoyancy or the density difference, Archimedes principle, okay, you can say.
Okay.
So that happens in reality. In reality, that upwelling happens. So the coastal regions, as the upwelling happens in the coastal regions, the water is cooler compared to the normal value. Now that happens in a very narrow region, and in the narrow region, because of course if the coast is there, it will always, it cannot happen towards the large region along the coast, so it will happen to a narrow region, or it will be confined to a narrow region, and models cannot capture that because of their low resolution. Suppose a model has a resolution of, let's say the resolution is 1 degree, that is 100 kilometer, and the upwelling happens within 100 kilometer, then the model will fail to capture such phenomena. That's why the model, whatever is given, the whatever it is giving is having higher value compared to the normal or whatever happens in the reality. So that is one bias. Another bias is also negative bias or lower temperature in the interior part of the ocean. So in the interior part, the model gives lower temperature compared to the observed value. These are some model biases, and yeah. So that is one question. Just if you are asked why it happens, and
Actually, why is the ocean temperature higher than the bottom part? Why is it? Because is it because radiation is absorbed or something? Absorbed? Or
uh, you are telling why the temperature is lower in the bottom part compared to the
yeah, the
surface.
upper part. Yeah.
Yeah, in the surface, first of all, let's suppose that if there is something, if it is a stable, I mean, if the upper temperature is higher and lower temperature, I mean, the temperature in the deep ocean or in the deeper region of the ocean is lower, then it is a stable system, first of all. So if there is any kind of instability, that will be removed by circulation. Fine. So, but also, apart from that, the upper part gets solar radiation directly, and
Okay. Okay.
due to the solar radiation, the light cannot penetrate beyond 100 meters or so. So the absorbed radiation mainly heats up the ocean in the top layer. It is, I think, called boundary layer or something. So
Okay.
boundary, yeah, mixed layer. I think it is called mixed layer. So due to the solar radiation, the temperature of the upper ocean is higher compared to the lower uh, ocean. And also,
Okay.
it is a stable
There is a
ocean.
there's a rotation also. Rotation of Earth also play any role in temperature,
Rotation of Earth in temperature.
ocean temperature, rotation of oceans.
Yes, it can play a role in the sense that, but it cannot play in the small scale. It will play in the large scale, because the effect of the rotation, that is only significant in the large scale. So if there is rotation, then there is Coriolis force, and centrifugal force is like not so much, but Coriolis force is important, and that force provides the geostrophic balance. It means if a circulation is rotating, then it is in perfect balance, though there are differences in the densities of the water. So that geostrophic balance provides one extra force or one extra kind of stability to the ocean. So even though the density gradients, the density gradients are not exactly parallel to the pressure gradients, the geostrophic balance can have a role in controlling the structure of the ocean temperature, or on the other hand, it can control the density also, because temperature is related to density.
Geostrophic balance. Uh,
Yes. What you asked? What is geostrophic balance?
yeah.
Oh, okay. Geostrophic balance is due to the rotation of Earth. There is a force on the moving object that might
Oh,
act towards the center of the rotating gyre or towards the outward of the rotating gyre. So
okay.
for that case, if there is some pressure gradient, or due to maybe the due to the effect of the rotation, the pressure gradient is formed. So the pressure gradient, when the pressure gradient exactly balances the Coriolis force, that balance is called geostrophic balance. So for example, if you are given a pressure gradient to some fluid, then the fluid will flow according to the pressure gradient from higher pressure to the lower pressure.
Low pressure. Yeah, that's
But in geostrophic balance, due to the force provided by the rotation, or let's say it is Coriolis parameter is, let's say it has some value, and if it is multiplied with the velocity, then it gives the magnitude of the acceleration. So that force is there and it acts opposite to the pressure gradient force. Then despite having the pressure gradient, the flow can rotate. So that is called the geostrophic balance, or not rotate, but it can sustain the pressure gradient. So that is called the geostrophic balance.
okay.
Very similar
Thank
to
you.
very similar to when you are rotating one bucket. You can try this at home. Take a bucket and fill the bucket with some water, some amount of water, and tie the bucket with a rope and rotate it fast. Now, due to your rotation, if you rotate it fast enough, the water will not spill out of the bucket. Though at the topmost point, it is against, the gravity is downward. Due to your rotation of the bucket, it provides one acceleration. Here it is centripetal acceleration or centrifugal force, you can say. So due to that, though the G or the gravity is acting downwards, it is sustaining the water in the bucket. So similar kind of balance that happens in the non-inertial frame, that happens with the ocean also. So I've just mentioned because even if there is some gradient due to temperature or maybe density, that can be sustained using the geostrophic balance. That's why I mentioned that.
Okay. Thank you.
So
सर इसी टॉपिक को हिंदी में समझा दो।
हाँ हाँ जरूर। हाँ, तो मैं बोल रहा था अभी, ओके, हाँ, ये हमारा हमारा सवाल था कि क्लाइमेट मॉडल्स शो हायर ओशन टेम्परेचर्स देन ऑब्जर्व्ड इन द कोस्टल रीजन्स। जो तट के किनारे जो इलाका होता है, वहाँ जो तापमान मिलता है मॉडल्स के द्वारा, वो हमारा जो सामान्य जो जो हमारा परिमाप किया गया जो तापमान है, उससे ज्यादा होता है। तो ये क्यों होता है, इसका कारण को हम ढूंढने का कोशिश कर रहे थे। जब हमारा मॉडल का रेजोल्यूशन कम होता है, मतलब वो ज्यादा ज्यादा जगह को, मतलब डिटेल्स को हम कैप्चर नहीं कर पाते हैं, तब क्या होता है कि जो तट के आसपास जो अपवेलिंग की होता है पानी का, मतलब जो नीचे वाला जो पानी है, वो धीरे धीरे वो ऊपर आता है, और नीचे वाला पानी ठंडा है ऊपर ऊपर वाला पानी से। तो ये स्वाभाविक प्रक्रिया है, ये चलता है हर एक तट के किनारे। तो इसके लिए तट के किनारे का जो पानी है, वो सामान्य रूप से जो पानी का तापमान होना चाहिए था, उससे कम होता है। पर हमारा जो मॉडल से उसका रेजोल्यूशन कम होने के कारण, मतलब सपोज आप मान लीजिए कि हमारा मॉडल का रेजोल्यूशन है 100 किलोमीटर, तो 100 किलोमीटर के अंदर जो हो रहा है उसको हम पकड़ नहीं पाएंगे। अगर ये अपवेलिंग, मतलब नीचे से ऊपर पानी आने का घटना अगर हम पकड़ नहीं पाते हैं, तो हमको ये लगेगा कि तापमान का भी जो अवनमन वो हम पकड़ नहीं पाएंगे, ठीक है। तो वो पकड़ नहीं सकते, इसके कारण जो तापमान मॉडल में मिलेगा वो सामान्य जो तापमान है उससे ज्यादा होगा, क्योंकि अगर वो हम पकड़ लेते हैं, अगर पकड़ सकते थे तो तापमान कम मिलता, पर हम पकड़ नहीं पा रहे हैं तो तापमान ज्यादा होगा, ठीक है। तो इसके कारण आप अगर तट के किनारे वाला हिस्सा देखेंगे तो वहां आपको तापमान ज्यादा मिलेगा। मैं एक तस्वीर दिखाता हूँ, आई जस्ट शो यू पिक्चर। जस्ट लुक एट द कोस्टल रीजियंस, तट के किनारे वाला हिस्सा देखिए, यहाँ जो मॉडल है वो पॉजिटिव तापमान दिखा रहा है, सो इट इज शोइंग पॉजिटिव वैल्यूज कंपेयर टू द इंटीरियर वंस। दैट इज द रीजन, बिकॉज एट मोस्ट ऑफ द कोस्ट्स द अपवेलिंग इज हैपनिंग, पानी ऊपर आ रहा है, बट आवर मॉडल इज फेलिंग टू कैप्चर दोज थिंग्स। मॉडल इसको पकड़ नहीं पा रहा है, इसके कारण बहुत सारे तट के किनारे, स्पेशली जहाँ आपका अपवेलिंग ज्यादा होता है, the regions where the upwelling is strong, quite strong, the models will fail to capture those phenomena. So that is a bias. That is a bias. I mean, though many models have tried to capture those things, it remains. So that is a bias. Bias means pakshapat. So it happens in the model. Okay. Is it fine, Ankit Mukesh?
Yes, sir.
Okay. Now the the next question is, how can you determine climate models, using climate models, that the global warming is a real effect, so it is really happening due to human activities? So for that it is very easy. So you have the model, so you have the control in the model, you can control different factors that contribute to the model. So in one case you just use the natural factors which can account for the temperature change or temperature variation in the earth. And in the second model, keep the natural factors, but include the human activities as well, anthropogenic factors as well, and see which one matches the observation better. So, very simple. If you are trying to prove something, then if you are trying to prove that A happens due to B, then first do not include B and see what is the result of A. And secondly, you just include B and see what is the result of A. So if on the first case it doesn't affect A, you will be sure that this is an effect of B. So for example, here people have used two types of simulation. The blue one denotes the natural modeling or the modeling due to natural activities. So which is volcanic, solar, and sulfur dioxide. What is this? Sulfate? No, sulfate is for anthropogenic. Anyways, volcanic plus solar activity. And in the second case, which is denoted by the red, it has both anthropogenic and natural factors into its consideration. So you can see that the red one matches very well with the observations. And you can see the pink line, pink shading. So that, I think that actually refers to the uncertainty. And that is actually also captured while you do the ensemble. Anyways, so they have taken some mean, or they might have given the 95% confidence interval. Anything is possible. I don't know the details. Anyways, but you can see that when the anthropogenic factors are taken into account, the results match quite well with the modeling output. So that is the study. I mean, that is the experiment, or that is the methodology you should follow to see the anthropogenic effect of temperature. तो I'll just explain in Hindi. So हम अगर मनुष्य द्वारा किया गया तबाही को देखना चाहते हैं तो हम क्या करेंगे? हम अगर निश्चित होना चाहते हैं कि जो तापमान का जो वर्धन हो रहा है वो मनुष्य के कारण ही हो रहा है, उसके लिए हम क्या करेंगे कि हम एक बार मॉडल को चलाएंगे जिसमें हम प्राकृतिक जो कारनामे हैं उसको हम अंतर्भुक्त करेंगे, और उसके लिए तापमान कितना बढ़ रहा है वो हम देखेंगे, जो यहाँ जो नीला सा रंग है उसके द्वारा सूचित किया गया है। और दूसरे क्षेत्र में हम क्या करेंगे, ये जो प्राकृतिक जो विषय है उसको तो रखेंगे ही, उसके साथ साथ मनुष्यों के द्वारा जो हो रहा है, जो तबाही हो रहा है, उसको भी हम अंतर्भुक्त करेंगे और दोनों मिला के क्या हो रहा है, वो क्या उत्पादन कर रहा है, वो देखेंगे। जब हम दोनों को एक साथ गणना में लेते हैं, तब हम देख पाएंगे कि जो हम हम जो पर्यवेक्षण किए हैं, काला सा जो यहाँ है, उसके साथ ये जो लाल सा, मतलब मनुष्य द्वारा और प्राकृतिक दोनों मिला के जो हमारा तापमान निकला है, उससे ये बहुत अच्छे से मिल रहा है। ठीक है, तो इससे हम पता कर सकते हैं, इससे हम निश्चित हो सकते हैं कि ये मनुष्य द्वारा ही किया गया है। अगर इसको हटा दें तो ये नहीं होता, तो तापमान काफी नियंत्रण में रहता और ज्यादा नहीं बढ़ता। ठीक है, इज इट फाइन अंकित, मुकेश?
Yes, sir.
Okay, so yeah, this is just the image for the two graphs. Now, if any one of you pursue model studies, then you can do a lot of experiments with the models. So you can actually, if you can set the model well, then you can actually publish a lot of research papers. Just you have to set the model cleverly, and using the basic logic, you can find which factor is important for what process. And if you can do this, then you can find a new research, because there are plethora of possibilities to get different outputs, and you can show factor 1 is important, factor 2 is important or not important, whatever it is. So setting the model is a laborious task, but after that, if you have the control over the model, then you can take the control of different variables, different factors of the model, different parameterization schemes also, and then you can determine what is important for capturing what. Okay, so that is if you know modeling, that is a very good advantage in pursuing research into this field, at least. Hmm. Next, okay, we have just shown this slide. So there is a CME 5 case, CME 5 scenario, sea surface temperature. CME 5 represent Climate Model Intercomparison Project, CMIP, and it is the 5th generation. So they release different editions for the model. That's why, um, so that's why it is named upon different cases. Okay. So, uh, so here you can see in the interior part of the ocean, it is underestimating the temperature, and toward the coastal regions, it is overestimating the temperature. So coastal is for coastal bias. I don't exactly know the reason for the lower temperature in the interior. They might be they are missing the solar radiation or some factors, but it is not a very strong bias, but they are continuously having lower values in the interior of the ocean. So these are two biases that is found while modeling the sea surface temperature. So we should be aware of the model bias while dealing with the model. So there are some factors which are always present in the model, and if we can identify those factors, we can get rid of the bias quite well. And if we can explain those factors, that is also a good piece of study. Okay, so now for determining weather and climate, we will just mention a few models, so which are used for determining the future scenario evolution in weather and climate. The first one is DNS. DNS stands for Direct Numerical Simulation. For that, I need the Navier-Stokes equation, but I have to get confirmation. So, do you know about the Navier-Stokes equation? Navier-Stokes equation, how many?
The equations governing the motion of fluids, right? I'm not so
Right,
sure.
right. It is the combination of the momentum equation and the continuity equation in the fluid. So it is basically the Newton's second law of motion, but applied to fluids.
Okay.
So momentum conservation and mass conservation. So these are the two basics of Navier-Stokes equation, but it is commonly used in fluids because in fluids there are different processes which are important. But essentially there are only uh, momentum conservation and mass conservation. Ankit Mukesh, do you know Navier-Stokes equation? Or have you heard of that? If you don't know, you can also just tell. I will just mention it once because it is a big field of research, so I cannot explain it. But at least for proceeding, we can just give a hand waving explanation. So
So could you explain it? Just
yes, I'm just getting the starting point. अंकित मुकेश आपको आप सुनिए है ये नावियर स्टोक्स इक्वेशन में कहाँ से बताओ?
जो नेवियस्ट इक्वेशन होता है सर, वो मतलब जो तरल पदार्थ होते हैं उनको वर्णित करता है
सही कैसे वर्णित करता है?
समीकरण के द्वारा।
क्या?
जो नेवियस्ट इक्वेशन होता है वो मतलब तरल पदार्थों की गति और दबाव के बीच जो रिलेशन होता है उसको शो करता है।
सही सही सही। और एक चीज होता है संरक्षण पदार्थ, तरल पदार्थ का संरक्षण जो मा मतलब क्या मास को क्या बोलते हैं? तो जो मास होता है उसका जो संरक्षण सूत्र है उसको भी एक साथ लेता है। तो तीनों मिला के कंजर्वेशन ऑफ मोमेंटम, कंजर्वेशन ऑफ मास, ये सब लेके आप सही बोलिए, एकदम एकदम सही। सो या सो अर्जुन, दिस Navier-Stokes equation is basically
I think is conservation of energy also there.
no, in Navier-Stokes equation conservation of energy is not there. So
Okay.
Navier-Stokes equation is the conservation of mass and conservation of momentum equation. And from the conservation of mass and momentum equation, they try to derive the conservation of energy equation for different systems. So that is a byproduct of that.
Okay.
Yeah, I mean
Okay.
it should follow the conservation of energy, शक्ति का जो संरक्षण सूत्र. So, but it is actually follows from the mass and momentum conservation equation. They do it in that way. So suppose you are given initial velocity or initial distribution of the mass and after in the fluid. So after that, after certain time, given pressure, दबाव का क्षेत्र, given the fluid, the flow velocity, प्रवाही का कैसा चलन हो रहा है, that one, and also given the external forces, बाहर से जो शक्ति दबाव आ रहा है. Yeah, so taking into consideration, we just try to determine the velocity of the fluid and also maybe the density of the fluid. So that is the Navier-Stokes equation.
Okay.
Okay. So basically, what we do is we try to solve the, see, if we solve atmosphere is a fluid, ocean is a fluid. Now, if we can somehow solve the Navier-Stokes equation completely, then there is nothing left. Okay, you will get the result. You will get the result of for any type of fluid for both ocean and atmosphere. But the problem is we cannot exactly solve it. It is very laborious. It is computationally very expensive. So इसको गणना करना बहुत मुश्किल काम है, हमारे पास उतना कंप्यूटेशनल क्षमता है नहीं. So we try to do different methods. The first one is direct numerical simulation. So this is the most accurate form of solving Navier-Stokes equation, where the full Navier-Stokes equation is solved. So there are processes like turbulence, diffusion, etc., that are all taken into account for this direct numerical simulation. And it covers the full spatial and temporal ranges. So it takes very small value of the time step and also the full resolution of the grid size. Okay, and it tries to solve the equation in its. I will just try to show the Navier-Stokes equation. It will be helpful. Yeah, so that is the equation. So that is the first equation in which they are telling that this is the acceleration du dt is that is the um, summation of the viscosity and the pressure term. So they have taken both into account, and A is the external force, I think, or A represents body acceleration acting on the continuum. So external, it is external force or external acceleration. So basically, this is the equation of the second law in Newton's second law of motion, but for fluids. So, and this one is the conservation of mass. So they are telling that whatever mass is entering, that same mass will exactly exit through a control volume to the maintain the continuity. So that is this Cauchy momentum equation. So where is the mass equation? Yes. So this equation. Let me just find the continuity equation. Okay, there is one form of the continuity equation, divergence of u is equal to 0. So basically there are two equations, one is for mass and another is for momentum. And that's how they determine the motions of the fluid. So yeah, so continuity equation for incompressible fluid. So they have just determined the change of mass with respect to different processes, maybe the convergence or the divergence of the fluid and also the local change of the density of the fluid. So yeah, whatever mass cannot be created or destroyed, that is the basis of the continuity equation. So in these two cases, they assume those two equations, and using that they try to solve the full motion of the fluid in the direct numerical simulation. So they do not assume any kind of parameterization. So whatever is present in the grid or whatever is present as the initial condition, they take it completely. That's why the full spatial and temporal ranges of the domain are resolved. That is the most accurate form of solving Navier-Stokes equation. Okay, now if you can solve this, let's say you solve the DNS for the whole world, then you are done. So you don't need any type of extra equation for atmosphere or any extra equation for ocean. So you can get the exact solution. So that is just a fluid mechanics problem. But that is not possible because it is computationally very expensive. So DNS is very difficult to compute, even let's say for 1 kilometer plus 1 kilometer domain, it is very difficult to compute. That's why they use different type of proxies or parameterization for approximating the subgrid scale processes. Subgrid scale process means the processes which happen in the smaller scales, but we do not exactly capture it, but we give some proxy or give some values which might be close to the originally obtained value. So the second case comes for the large eddy simulation, LES. So mathematical model is used to determine the turbulence in the smaller scale, because in the smaller scales, the turbulence effect is there, but it becomes computationally very expensive to resolve the smaller scale processes due to turbulence. That's why the larger scale eddies are actually solved using the Navier-Stokes equation. That is the complete solution, exact solution. But the smaller scale eddies are parameterized using subgrid scale model. So let's say there is a subgrid scale eddy, and due to that eddy, you get some kind of output into the next grid. Then now that output is not exactly calculated, but it is given some simplified value, assuming the conditions of the surroundings. So that's how this works. So that is the parameterization. Okay. One example of parameterization is, uh, let's say, for example, I am giving, for example, of clouds. Now, suppose you get some clouds in the sky. Okay. Now, in the sky, you get some big cloud, and it is raining over your region. So let's say you live in a city which has a size of 10 kilometer cross 10 kilometer. But our model cannot capture the 10 kilometer cross 10 kilometer resolution. So it cannot exactly give what amount of rain will occur at each part of your city. So, but using the size of the cloud, let's say a cloud is coming towards your city, then they will say that, okay, I will just determine the height of the cloud and the width of the cloud that much, and I will predict that, okay, it will rain 100 millimeter in 2 days in your city, but they cannot tell you exactly what amount of rainfall will occur in each part of the city. So there will be different values of the rainfall in different parts of the city. But due to rainfall also, there will be some convective circulation. There might be some latent heating due to the rainfall, or basically the phase change of the water vapor to rainfall. And there can also be temperature drops. But they will assuming the bigger size of the cloud, they will assume something and they will input it in the next grid. So they will miss the information at local levels, but they will consider the aggregate effects of the clouds. That might be wrong, that might be slightly wrong, that might be largely wrong also, but they will assume that. So that is parameterization. So in LES, they try to parameterize the smaller scale grids, eddies, which are known as subgrid processes. Okay, and there are different models for parameterization. So people have.
Could you explain parameterization again? What is it?
Yes, for parameterization, whatever we do is we cannot exactly solve the process. Suppose a process is happening, a cloud is going towards a region, and we don't know how much it will rain in that particular region, and what will the effect of the cloud be in that particular region. So we try to do, we try to say that we will take the cloud as per our uh, greatest resolution, our highest resolution, and then we will predict how much it will rain in your area or how much cloudiness it will be here. So suppose uh, there are two regions. So suppose there are, okay, let's say there are four regions. There are four regions in a, I will just try to draw. So suppose that is one grid, and we can only say for the cloud that where the grid has cloud or it doesn't have cloud. Now suppose there are four regions in the grid. So I will just try to draw using some dashed lines. So here are four regions, and now one cloud comes here. Now due to the lack of our knowledge about the grid, the weatherman or weather scientist will assume that that grid is full of cloud, and they will predict that it will rain in all the four regions, because all the four regions are included in this particular grid. And in this particular grid, they will assume that the whole grid is full of cloud and the associated processes due to the cloud. For example, let's say the radiation due to cloud, the solar radiation will be blocked, and the outgoing long wave radiation, that will be also blocked, and also there will be latent heating due to the cloud or the rainfall. They will all take into account about the whole box. Okay, so the effect will be completely contained in the whole box, and that's how they will insert that value of whatever output is obtained using the processes in the whole box into the next grid, maybe the surrounding four grids, whatever it is. And then they will
Okay.
try to calculate the processes of the next grid, so that micro details or the subtle details of this grid is actually exempted, but they take it as a whole, that it is completely cloud filled and it has rained, something like that. So that is a very simple example of parameterization, but there are different processes for parameterization. For example, let's say there is a wind is flowing over the ocean, then due to the wind there will be some drag forces inserted onto the ocean. Now there is a bulk aerodynamic formula for the drag force for the wind on the ocean. So that is taken into account. Also for solar radiation, let's say there is a solar radiation, whole solar spectrum. Let's say the spectrum is like that. But we cannot exactly resolve each and every wavelength for the solar spectrum. So we assume that into that particular range, that much of solar radiation will be obtained. So that is another type of parameterization. And convective parameterization. For convective parameterization, they will assume that the rainfall is proportional to the amount of moisture in the atmosphere. So if there is more moisture, and they will subtract it to a critical value. So higher the moisture, higher the rainfall rate. They don't know about the micro details. So you have often observed that in your city, some parts often receive higher rainfall compared to your part, or lower rainfall compared to your part. So it doesn't rain uniformly in all the areas of your city. But for weather or modeling purpose, they will take the whole thing as one single value in the grid, and they will try to approximate the value using simple equations, which is not the exact Navier-Stokes equation. So that is the essence of parameterization.
Okay. Thank you.
Okay,
Okay.
Ankit, Mukesh, is it clear?
Yes, sir.
Okay, so yeah, so in large simulation, they will use the parameterization for smaller areas because they are difficult to solve. And larger eddies will be exactly solved. And the outputs of the smaller eddies, the parameterized smaller eddies will be taken as the inputs of the larger eddies. And that's how they will solve the large eddy simulation. So it is less accurate compared to DNAs, but more computationally efficient, or computationally more convenient for. Similarly, there is another model, CRM, cloud resolving model, which is often taken as a coarser resolution, so 1 to 4 kilometer. But you know that in 1 kilometer in clouds, many things can happen. So there might be development of clouds in between. There might be lightning in certain places, but it might not lighten in another places. Many processes are there. There might be heavy showers in some, let's say 500-meter radius. You also know about tornadoes. So these are very small events. So, but we cannot exactly resolve those processes. Anyways, so they again subgrid, they often parameterize the subgrid scale processes. That is another example of the parameterization, but they are efficient in giving the rough estimation of the idea. That's why our weather predictions often cannot give us exact results. Suppose they say that it will rain very heavily in the whole uh, region of, let's say, Jaipur, but it might not rain in the whole region. There might be higher rainfall in surrounding northeast part of Jaipur, and it might be relatively dry in the southwest part of Jaipur, like that. So they're cloud resolving models. But one benefit is they can cover a lot of ranges. So they can cover 100 kilometer to 1000 kilometer in this particular model. Next comes the numerical weather prediction model that uses the atmospheric data from the observation. So that is real data. And they also use the physical laws to simulate different conditions of the predictions. And again, it has to parameterize the small scale processes. And yeah, two examples are cloud microphysics and turbulence. And there comes the global circulation model, the general circulation model, or global climate model, which hey, it has to parameterize a lot of things. So it cannot give us regionally accurate results, but it can give us an overall trend of the model, overall trend of the Earth. So no single model can resolve all the skills. Let's say maybe 1,000 years after today, after this year, we might get a very efficient supercomputer that can solve the DNS, direct numerical simulation, for the whole Earth. But that day is too far. Before that, we have to rely on the parameterization. That's why how well, with how much clarity, or how much cleverness, or how much efficiency they can parameterize certain small scale things is still a field of research. Otherwise, I think that one day, if we can perform the direct numerical simulation for the whole world, the use of parameterization will not be there. So, but yeah, I mean, there are always quantum scale processes that you that we cannot determine. So quantum physics is always a guide. Yeah, so in our climate models, we use GCM to understand the trends of temperature, the trends of rainfall, maybe trends of sea level for the future climate scenario. So here we can see that hierarchy of, oh, sorry. So yeah, is it clear?
Yes, it's clear.
Yeah,
It's clear. It's clear.
okay. Ankit Prakash, is it clear? We're just talking about
Yes, sir.
hierarchy of models. तो हमारा रेजोल्यूशन जब घट रहा है, रेजोल्यूशन जब बढ़ रहा है तो हमारा कंप्यूटेशनल पावर भी बढ़ना जरूरी है, पर हमारे पास उतना अब तक है नहीं, तो इसके लिए दिक्कत होता है। इसके लिए ही हम पैरामीटराइजेशन का इस्तेमाल करते हैं। जो बड़े बड़े क्षेत्र के लिए मॉडल होते हैं, जैसे ग्लोबल क्लाइमेट मॉडल, उसका रेजोल्यूशन कम होता है और पैरामीटराइजेशन का भी बहुत ज़्यादा इस्तेमाल होता है, पर वो करना ही पड़ेगा क्योंकि हमारा गणन क्षमता उतना है नहीं अब तक। धीरे धीरे उन्नत हो रहा है, पर वो दिन कब आएगा पता नहीं, जब हम पूरा विश्व का ही डीएनएस, डायरेक्ट न्यूमेरिकल सिमुलेशन और नावियर स्टोक्स इक्वेशन का समाधान कर पाएंगे। Okay, so just an example with a graph. I think that is a better representation of this model scaling. So DNS has very small scale, millimeter or centimeter, and the domain size is less than 1 kilometer, because you cannot perform for more than 1 kilometer. The computer will crash. And there are partial model, large GD simulation, which can resolve 10, 20, or 50 kilometers model, and the grid size is a few centimeters to 1 meter, or maybe 1 kilometer also. And CRM, cloud reserving model, so it's centered about 1 kilometer of size, because they assume that the cloud size is 1 kilometer, and within 1 kilometer, before or I'd say less than the 1 kilometer resolution, no special thing happens, and they can parameterize that. And then there comes WRF type of model, weather resource forecasting, which is even lower resolution or higher coarse grid size, 10 kilometers or so. And the highest model grid size is for the GCM, global climate model. And also it has the domain size of the whole earth. So that is the purpose of this. So they can predict the overall trend of the earth, the climate scenario of the earth, but on individual scale, it will badly fail to understand the future conditions. Okay. Okay, now we will just discuss a few things about the possible scenario, just for that is just for attraction. So we don't know whether this will happen or not. So what can happen in the future cases for India? For India, there are different scenario for temperature, rainfall, and humidity. So the models predict that there will be increase in number of heat waves, also the duration of heat waves, and also increase in the minimum temperature. So the overall increase in temperature, that is one trend, with commencement of more suffocating or more unbearable conditions due to heat waves, and increase in rainfall over many places, that is due to temperature, increase of temperature, and there will be more water vapor in the atmosphere. So for India, it shows that there might be increase in rainfall in many places, especially over the northwest region. So in Rajasthan, in Punjab, Haryana, or Maharashtra, Madhya Pradesh, this type of areas, or Delhi, maybe they might witness higher rainfalls along with the future scenario, future cases. But decrease in rainfall over Keralam. So they assume that there might be decrease in rainfall because the monsoon jet that actually hits Kerala, it is shifting little north day by day. So the rainfall in Kerala has decreased in the past few decades, and it will also continue to decrease over the years. But actually the problem is the rainfall in Kerala is quite high, so the decrease of rainfall is not exactly realizable or visible now, but maybe after some years it might be noticeable, and the flora and fauna of the Western Ghats might also change, so that can happen. In northwest India also the rainfall might decrease, and due to the shift of the westerly current, westerly jet, there might be increase in rainfall on the Konkan coast, that is north of Kerala. And overall, there will be increase of extreme rainfall events. So heavy rainfall events will occur in short time span. That is one scenario. That is one possibility. And also there are chances of increment in the moisture capacity or in the relative humidity. So if it happens, then the places will experience more uncomfortable weather, because if temperature is combined with humidity, then the weather becomes more uncomfortable. Okay, so any question on this?
Hello?
Yeah, any question on this?
Mm.
Okay. Now we will just look into the temperature in 2025. That is just a case study, so it might not reflect the overall trend, but it is just a case study in 2025 because it was an exceptional year. It was quite hot, basically the last year. And reference period is given as 1991 to 2020. So increase or decrease in temperature is with respect to that particular reference period. So you can see the polar regions or the regions with higher latitudes experience lot more warming compared to the tropical regions. The tropical regions are also warm, but that difference is more pronounced in the higher latitudes. So that is an artifact of this climate change, that the polar regions or the Arctic and subarctic regions will be more amplified in terms of temperature perturbation. So they will experience more increase in the temperature. That's why the polar ice is also melting at a rapid rate. So this is of a concern. It's called Arctic amplification. And yeah, there are actually reasons behind that, because the effect of the albedo is higher in that region. So once snow starts melting, then the albedo becomes really uh, high, or it
Hello?
changes drastically in this region. Okay. Ah, actually, 2025 was a La Nina year, so the sea surface temperature in this Pacific Ocean region was less than normal in the Eastern Pacific. Still, it showed higher temperature anomalies or positive temperature anomalies in many of the parts of the world. So this is a concerning signal of our climate change or global warming. Okay, next slide is about the parameterization. We will talk a bit about the parameterization schemes and different parameterizations which are done. In an atmospheric model is a method of replacing processes, okay, that are too small scale or too complex to be physically represented in the model by a simplified process. And so, yeah, whenever we cannot resolve the processes beyond certain resolution, the parameterization is used. For clouds, cumulus parameterization is used, where the clouds actually have size of less than 1 kilometer, but the grid boxes are having resolutions of around 10 kilometers, though they are trying to develop kilometer scale model, but I think it is not completely active in all the operations. So the subgrid processes, let's assume it is below 10 kilometers. So in the clouds are considered as parameterized values. So that's how they do the cloud parameterization for cumulus clouds. Then comes the radiation and atmosphere surface interaction. There are plenty of parameterization. We are just explaining a few. The solar radiation reaching the ground, that is a very complicated function that depends on the solar constant is there, but after that there are different layers of the atmosphere, and also the medium is rapidly changing from the top of the atmosphere to the ground. So there might be absorbance, there might be scattering, there might be reflection, there might be refraction, different processes are there. So it depends heavily on the atmospheric path and the structure of the ground also. So if the ground is flat, then it will get the solar radiation at some particular angle. If it is curvy or if it is rugged, then the solar insolation will have some other value. So that things should also be taken into account, but we cannot exactly resolve all of these processes. For example, the details of the atmosphere or the details of the terrain. So that's why these are also parameterized, the radiation that reaches the ground. Similarly, the transmission is also transmission or the radiation, transmission, reflection, refraction, scattering. These also depend on the molecular level interactions. So we cannot resolve those molecular level interactions. So better we try to parameterize using simple formula. That depends on the density, the optical path. Okay, so this extinction coefficient, that is a scattering and absorption of the molecule. So that parameterizations are used for the radiation. And after this radiation is parameterized, we can do energy balance. Okay. For air quality is also parameterized. We cannot determine exactly how much particle is present of a particular type of pollutant. We cannot chemically resolve all the pollutant in the atmosphere. It is a tedious job and almost impossible job. So we look into um, different properties of the materials or different properties of these molecules, and depending on the density or the presence, we determine how much of the pollutant or how much a particular type of molecule is present in the atmosphere. And air quality forecasts depend on that. That's why it also requires parameterization. So let's say an air is very dusty, then the intensity reaching from the source to the sink or from the source to the receiver, that will be affected by the amount of dust in the air. So they will calculate the incident and the received intensity, and they will determine the value of the concentration of the particular dust or pollutant. In ocean also, AD parameterization is done because the grid size is not enough to resolve all the ADs, especially the smaller ADs, but it contains some amount of energy. So it is important to give some values. We cannot just ignore those ADs. So what people do is they take into account the effect of ADs using different parameterization schemes. There are scientists have developed different parameterization to consider the, the outputs of the ADs, and that parameterization is applied for activating the sideward grids or for continuing the equation in time and space. Okay. Yes, so any questions on parameterization?
No, it's clear.
Okay. So I just recall something. So do you know about the parametric form of a circle, equation of parametric form of a circle?
The equation is x square plus y square is equal to r square.
Yes, that is true. But they use a parameter for describing the circle. So I think that is the
I
simplistic
forgot.
form.
Yeah, yeah, it was there when at school, but I forgot the form.
Okay. So what is the equation of circle? Can you tell me? X squared plus
Y square is equal to r square.
r squared. Okay. Just take x equals to r sine theta, y equals to r
Yeah,
cos theta.
r cos theta. Okay, fine. It adds. Okay, yeah.
So basically the parameters are r and theta.
Yes.
Suppose an object is moving at almost a circular position, a circular path,
Okay.
but you cannot precisely determine the x and y values on the circle because somehow maybe your grid is not efficient enough to determine the
X and y are Cartesian coordinates, right? So,
Cartesian coordinates. Yes. But you can see that it is evolving around a path. So you know the radius. So somehow you know about the radius, but you don't know about the exact x and y points. Now,
uh,
And you know that it will move in a circular, so the theta value will change with respect to time. So if you
Yeah.
know the radius and you know that the theta will anyways change with respect to time, so using this single value of the radius, you can track the whole path.
Yeah.
So like for parabola, there are also forms of the parameterization. So let's say y equals to some t square, x equals to some alpha t, and using that, or let's say t or something, depends on the coefficient, you can determine the path of the parabola. Just vary t, you vary a single parameter t, you will get the
Mm.
path, you will get the family of the parabola.
But for circular, there is no simplification. I mean, it is x and y are two variables, and r and theta are two variables, right? So
Yes, no. That is present for everything. So for determining a 2D system, you need some 2D two
oh,
variables.
yeah.
So there is no simplifications to that. You cannot determine uh, the value of a 2D system using only one variable. That's not possible. So because I just recall that we read about the parametric representation of circle, sphere,
Okay.
ellipsoid, ellipse, like that.
Actually, Earth is an ellipsoid, is it, or is it a sphere?
Earth is a uh, geoid.
Okay.
It means it has the form of, you can express Earth in terms of spherical harmonics. So
Okay, you said ellipsoid, is it? Or
it is not ellipsoid. It is also not ellipsoid. Ellipsoid means you have three axes and you can determine uniquely the Earth using the three axes. So yeah, I
yeah.
mean, ellipsoid is a better approximation of Earth than circle. That is true. But still it is not ellipsoid. So it has this terrain, variation of the terrain. So yeah, of course, ellipsoid is a better approximation where the radius at the equator is higher than the radius at the poles, from the poles. So that is true, but it is not exactly ellipsoid. So geologists, geography people call it geoid. And there are people who study the gravity of Earth at different places due to the different depths and also the materials present in different areas. So they try to express the earth in terms of spherical harmonics. So spherical harmonics are harmonics on sphere, but these have dependence on theta and phi. So let's say you can express earth as a function of r, theta, and phi, where all the three variables r, theta, and phi are variables. They vary with respect to what? They vary with respect to different locations on earth.
Latitude and longitude. Is it?
Yes, I mean r is a function of theta and phi.
R is a function of theta.
The radius from the center is a function of theta and phi. That is I can describe. So that
Why is R a function of theta and phi?
because at different latitude and longitude you have different radius from the center of the earth.
Yeah, if it is not a sphere. Okay, fine. If it is not a
It
sphere,
is not,
is it?
yeah. So you can assume earth as a summation over a lot of this spherical harmonics.
Okay.
So that's how it works. So that's how they try to describe. Yeah, you are assuming different spheres, but with different weightage and also, I mean, not spheres, but
Spherical coordinates.
harmonics in the sphere. So it varies with respect to theta and phi, and express it as a summation of those spheres. So the largest mode is of course a sphere, or the greatest, I mean, the best approximation is of course a sphere, but there are small variations of the height of different places.
Okay.
So
But
okay,
if atmosphere is taken into account, is it still spherical harmonics or okay? Thickness of atmosphere is constant, right? So it will be
no, it is not constant, but they use
across
people.
the
They
surface.
No, it is not constant, but they take spherical harmonics.
Okay.
It works well, spherical harmonics, as long as your shape is very close to sphere and it has periodic boundary conditions, the spherical harmonics works quite well.
Okay. Thank you.
So yeah, so I have listed some questions. Why do climate models not always predict regional climate change properly? Yeah, of course, the data at the regional details are not available. The resolution is not so high, and also the computational power is very low for getting the exact forecast for the regional level. I cannot exactly tell what is the situation in Chennai, what is the situation near Ernakulam, something like that. What will happen after 50 years? We cannot tell that. Many people demand that, claim that, but that is not possible. Second question is, why is predicting melting of Greenland ice sheet difficult? It is difficult because the processes are non-linear. For example, one ice sheet is broken and it divides into two ice sheets, or it collapses into the ocean. So we cannot determine these sudden chaotic processes. So these are non-linear processes we cannot model. There is another question: what is model tuning and why is it necessary? So adjusting the model parameters to match past observations, because if we can match the past observations, we then only we can be sure about the present and the future, because past is the backbone of present and present is the backbone of future. So it also is performed to match the physical conservation laws. Now, downscaling is an interesting topic. Many people are working on downscaling. They use different methods to downscale. Downscaling means creating higher resolution image from lower resolution image. Suppose you have a 10 cross 10 kilometer grid box and you want to extract information in the 5 kilometer range or 1 kilometer range from the 10 cross 10 grid box. So that is a very magical phenomena, but magical process, but that is actually done. So in statistical downscaling, the statistical relationship is developed from the model output and the historically observed climate data. So you might have, if you weather stations in that particular 10 cross 10 kilometer and you have statistical data. And from that data, you assist the model with the data and you will get some relationship between the data and the regions inside the grid scale. So from that, they can produce site specific or high resolution data that is applicable for local regions. Another question is, why are the temperatures more predictable than the rainfall? So temperatures follow a simple law of the conservation of energy. That's why it is little easier to predict compared to rainfall. We don't know where it will rain, how much exactly, because it involves a lot of subgrid scale processes. That's why, and it doesn't have exact conservation law. So many such configurations can match one particular output for the rainfall. That's why the rainfall is not that easy to predict. But for India, for Indian regions, the rainfall is very important rather than the temperature. Now comes the topic of cascade of uncertainty. So in our modeling, there are different layers of uncertainty which can accumulate together to give us higher uncertainty or to make our forecasts poorer. So there are different uncertainty at different levels which eventually add up to give us the greater uncertainty. One is the scenario uncertainty. So we do not know, this is just an example. We do not know how much emission of carbon dioxide will occur in the next 5 years. That depends on the policy of each and every country. We do not know what policies they will adopt, how how much discipline they will show, or how much emission they will make. That we don't know. So it is a scenario uncertainty that is out of control, completely out of control. Model uncertainty depends on the different models. Accuracy might be high, the accuracy might be low, but models always have uncertainty. So yeah, for example, rainfall versus height of the river. So the model can be good in capturing the height of the river with respect to rainfall, taking into account the absorbing water by the soils or the distribution of water in the nearby areas. One model can be poorer, where it can just tell that okay, if it rains 5 centimeter, the height of the river will also increase by 5 centimeter. So there are different hierarchy, different qualities of the models. Downscaling uncertainty, though we are trying to downscale or get the regional value in a final resolution, there might be inaccuracies always because we don't know the ground truth. We're just assuming that using statistical relationship and also dynamic relationships. That's why the downscaling uncertainty is also present. It is always present in this process. Nowadays, they are using artificial intelligence and machine learning to improve the downscaling process. So yeah, for that case, for that reason, the regional prediction becomes difficult. And this is impact model uncertainty. So yeah, so the physical inaccuracy, missing interactions, that is the fault of the model actually, that makes the prediction different from the reality. So these are the cascade of uncertainty or different layers of uncertainty that eventually accumulate to give us poorer predictions. Just an image for this particular from this particular paper. The model uncertainty decreases in future cases, and but the scenario uncertainty increases. That is the highest uncertainty, and internal variability that is initially present, but that decreases with respect to time. Same here, the model uncertainty decreases. That is for the global, and that is for the British Islands. So this particular region, internal variability is higher than this previous slide. Sorry, the previous picture. But the scenario uncertainty increases with respect to time because we don't have control over the scenario, what will happen. So that becomes the prominent uncertainty in the future times. Okay. Then a few facts on climate models, just for some takeaways. Okay. So that we have discussed to predict temperatures than rainfall due to signal or signal to noise ratio. So that's higher in temperature, lower in rainfall, or the signal is stronger in temperature and lower in weaker in rainfall. And variability on a longer scale is captured better than variability on a smaller scale. That might sound surprising, but for climate models, that is true. So we can tell that after 20 years, the temperature will have a range of plus minus, let's say plus 1 degree Celsius from now. But we cannot exactly say what will happen on the next year. Let's say in next year, it might become quite cold. It might become excessively warm, but we cannot exactly predict that. But on a 20-year scale, as the mean effects are there, so we can say that the average temperature will be beyond within this particular range on a 20-year scale. And yeah, we have also discussed about the regional scale, the challenges in the prediction of the regional scale. The challenge is the higher resolution. We don't have higher resolution data, and initial conditions are also not possible to uh, consider beyond a certain estimation, certain value. So these are two things required to predict the climate on a regional scale. Uh, yeah, so wherever we run the climate models, we have to always verify the models using the past data and the present present climate conditions, because these are the two certain things that we can always trust upon. We don't know the future, but we know the past and we also know the present. So if our models can capture those present and past scenarios, we can assume that it is working quite well to predict the future scenarios as well. And yeah, just example of the Earth system models or comprehensive models. They couple different aspects like atmosphere, ocean, sea ice, and land surface, and also the effect of the vegetation, also effect of urbanization. This type of things they take into account to simulate the whole Earth system. So yeah, so there are different components of climate model: ocean, atmosphere, coupling between ocean, atmosphere, ice, land ice, sea ice, coupling between this ice, ocean, and atmosphere, and also the vegetation. So these are a few facts in climate models. And now we will just conclude with two pictures of the change in temperature in the future case. I think that is the change in temperature since the mid 19th century. So the present temperature minus the temperature in the mid 19th or 1950. So we can see that in the polar regions, the temperatures have increased excessively. That is called polar amplification. And there is a increase in Indian region also, but the increase is not that much. But there is increase. There is increase in temperature. Actually, there is increase in the whole world. Almost the whole world there is an increase in temperature. But in the polar region, it is even more pronounced, the polar amplification. And also, we are worried about that because that will melt the sea ice and also affect the Atlantic Meridional Ocean circulation that can affect the climates of uh, global spatial scales. And the last slide is about the change in the precipitation. Whatever we can see, the precipitation in the year of 2008, 2081 to 2100. So it is in, let's say, 60 years from now. So in that case, we will see that the precipitation will increase across equatorial regions in the ocean, also in the Sahara Desert, also in the most of the desert parts, it will increase. The rainfall will increase. And in the Indian regions also, we can expect an increase in the rainfall, but in the South Africa and also in the Amazon forest region, also in the southern European region, we can expect decrease in the rainfall. But overall, as it will accumulate more water vapor into the atmosphere, we will mostly see an increase in the temperature. So yeah, I think that was the last slide for today. So I will just ask for any questions.
Can I ask a question regarding the exam?
Exam, you can ask. I don't know whether I will be able to answer it. Yes.
Okay. Will formula sheets be given or should we learn the formulas?
Formula sheets. I think the if you use some difficult formula, then you would be given the formula. You don't need to remember things. I think that is the concept of the NPTEL. But I think you can ask how many sessions, except from this session, how many sessions do you attend in NPTEL?
No, I haven't. This is my first NPTEL session.
No. I'm asking about there are also sessions on Monday or Saturday or Sunday, right?
No.
There are no sessions.
Session. What do you mean by session?
I mean
Uh,
this discussion. Like today we are doing some discussion.
no, there for this course there is only one day,
Friday.
Friday. Yeah, for this
Oh,
course.
then I don't know. I get messages for discussions on Monday or Saturdays. I don't know what it refers to.
Oh,
Okay. Oh. Let us search. Huh?
okay.
Let us search. I don't know. This is also my first NPTEL. I mean, though I am a teaching assistant, this is also my first NPTEL course. So I think if you are given to, if you have to derive some difficult answers, you will be given the formula because whatever from I have experienced, if you have to use formula, then you will be given that. You are not expected to remember things. So NPTEL exam pattern. I don't know whether it would such TL exam pattern. What is this given? 3-hour proctored computer-based tests consisting of 52 course. 75% from the exam, 25% from the weekly assignments. Okay. Uh, I think that will be given. If you require some formula, that will be given. Right. For example, you are talking about the specific heat, this type of formula, right? What the temperature change would be given certain amount of heat, or Lewis model, what is the temperature change, or what is the effective temperature of Earth, mean temperature, that things you're talking about, right?
Yeah.
Hmm. Okay, I will ask.
Okay.
I thought you have sessions on Monday or Saturday, Sunday, because I sometimes get messages on that there are live. So there are teaching assistants also. Because see,
Maybe for different courses they are doing, right?
but how? Why am I getting the message? Anyways, you don't get any message for that.
No, the videos are actually recorded by Sir.
No,
This
that I know. I also make the session according to the videos. So I also watch the videos, so that is fine. But
okay.
you have a NPTEL announcement page, right? Course announcement page.
Yes,
Just
yes.
ask there.
Okay.
Just ask.
No, in the forum. Are you telling in the
Forum,
forum
yeah,
or?
the forum, Google forum.
Okay, okay, okay.
Yeah, because I know there are teaching assistants who are actively involved in making the assignments. So they make the
Okay,
assignments, and I don't know properly, but they might also help in preparing the question paper, or professor might also do. But you surely ask there,
okay, okay, okay.
because yeah, it is of a serious concern, because you have to uh, pass the course or get good marks in that.
Yeah, yeah,
You know the method of the course. It will be in a center, right? NPTEL center.
yeah, yeah, yeah. We can register during registration. We can specify the centers that we want,
Okay,
the
okay.
choice.
Yes, okay. So, and I think from in that center, you have to go like, I think the JAM examination of GATE examination, this type of things.
Okay, okay,
So 3 hours, they are saying that multiple MCQ based or MSQ based questions, right? Yeah, fill in the blank. So it's online test.
yes.
Yeah, so just ask the discussion forum.
For
I
yeah,
actually lost access to that NPTEL course announcement, that what it's a login ID. That's why I cannot see anything.
okay, okay. That's fine.
Okay.
I'll ask in the.
Ask there. Okay, thank you. Any
Thank you.
questions? If you have any
No,
questions.
no,
Okay,
no. It's fine. Thank you.
thank you.
Thank you.